Okay, well, thanks to everyone that already joined. We will let the rest join as we progress through the introduction. Um, Before we begin, a few quick items. So everyone will get the webinar slides right after this presentation. We'll also share a recording of the webinar within 24 hours. And we will also upload this to our website in case you want to consult it or share it with interested colleagues. And last but not least, if after this presentation somebody has any questions that I couldn't answer or reply at the end of the presentation, we can always organize a one-on-one meeting and try to address that. So my name is Antoine. Some of you already know me. I'm a technical sales engineer for Seven Bel in Austria. And we will be beginning the day or the session by introducing the soundscanner technology, the soundscanner acoustic camera, comparing it with the state-of-the-art systems in the market. We will then quickly jump into the application section, which is the important part of this session, where we will be showing and presenting some use cases in building acoustics, in noise control, and in room acoustics. After that, we can spend the rest of the time for questions and some answers that I will try to provide. Okay, so without further ado, let's get started with the state-of-the-art and the state of acoustical imaging. So an acoustic camera, and this will be an extreme oversimplification, but an acoustic camera is an array of microphones which are placed in a measurement plane, in a so-called measurement surface. And we will assume that they all capture the same acoustical signals, except that they have phase differences, so that a certain sound front will arrive first to one side or the other of this array. Based on the phase differences between the signals that we will measure, we will be able to deduct, or by comparing these phases, we will be able to deduct an angle of arrival and the position of a source. There are two things that we need to consider when evaluating acoustic cameras, which are the size of the array and the amount of microphones that the array has. So these are the two main factors that will impact and determine the performance of an acoustic camera. The size of an array will determine its low frequency cutoff, so how low it can measure in terms of frequency, and also the performance at any given frequency, the precision at any given frequency. So if we want to separate sources which are sitting close together, we will need to have a large array at certain frequency. Then the amount of microphones will determine the dynamic range that's available to the instrument. And by dynamic range, we understand the ability to represent sources which are loud and quiet in the same picture. Okay, so there are systems which fulfill these two requirements. They are large, and they also have a lot of microphones, like the one you see on the left. The counterpart is that they are usually quite bulky, usually very pricey too, and also hard to set up, hard to use, and very complex in their hardware. Then there are much more portable instruments like the ones on the right, but they are very limited in terms of frequency response or spatial resolution. So the ability to precisely localize a source and showcase it in a compact way. The cameras like the one on the top, on the bottom right, are mostly thought for the ultrasound range because they are very, very compact. So how do we address these two problems? Well, the first, the idea that we came up with is a linear array, which is this arm that you see on the right, that we will rotate in order to recreate a virtual array. So with 5 microphones arranged in this linear fashion, and by rotating them, we're able to recreate an array of more than 400 virtual microphone positions by separating or splitting the measurement surface into more than 400 sectors. So with this approach, we have solved the size problem, given that we have a very large measurement surface, but still an instrument that is compact. It's a stick that you can put into that carrying case that you also see on screen and carry it around, and also the amount of microphones problem. This will result in an instrument that's easy to transport, but that still retains the full performance, and that's also a lot simpler in terms of hardware. Okay, We will then now show the three main components of this system, and then we can quickly go into the applications part. So the three main components of the system will be the rotating sensor, which basically just gathers audio data. It will send these 5 channels of audio data to a tablet. This tablet will be your interface with the device, so it will let you control the measurement, start it, stop the recording, set the measurement parameters. And it will also serve as your analysis pad. So that's where your projects will be analyzed. The computing part, though, will need to happen outside of these 2 components, and that will happen either on a cloud interface or on a laptop. So all the audio data at some point will need to go to this computing solution, which will go from audio data to acoustical image and then send it back to the tablet for you to be able to analyze it. All of this is interconnected wirelessly. Everything is battery powered and quite lightweight. The system that's on screen, the bigger one, is about 5 kilos when taken out of the case. Okay, so let's go to the main section of our presentation and start with the basic, or the most basic example that we're going to see today, which is a transmission analysis in building acoustics, a sound transmission analysis. This is a situation that most of you are probably already familiar with. We're trying to determine the transmission paths in a certain partition that separates 2 rooms, in this case, a meeting room and an office. To replicate a real-life situation where some noise is made in the office and filtering inside the meeting room, we will place a dodecahedron or omnidirectional sound source inside of the office, make it radiate white noise, and record that on the other side, on the meeting room, either with a sound level meter or with the sound scanner, in this case. This will let us understand how well that partition prevents sound from going from one side to the other. And with the sound scanner, we will try to understand how that sound is propagated from one side to the other. So this would be the traditional method. First, we would, of course, obtain a transmission loss curve. But we can also then start probing close to the wall in the near field to try to understand where most sound is being leaked through. And in this case, we found that in the corner on the top right, we had an increase in level for the problematic octave bands of 500 Hz and 1 kHz, which in the transmission loss curve showed weakness. So this first probing with the sound level meter lets us to believe that there is a problem at the joint between the window and the partition or in the corner. Still, this can be a bit misleading, given that we might be influencing the sound field with our own presence there. We might be running into a mode that's in that particular corner. There might be a reflection from another source on the window, etc. But a multitude of complications that make the conclusion not so obvious in the end. So we will now take the exact same measurement, the same viewing area, but with the sound scanner. And we quickly locate a completely different panorama. So now we see that the dominant source is actually located on a perforated panel on the top left for these 2 particular octave bands. There seems to be a reflection happening on the window, which could explain the augment in level in that corner. And given that we use the dynamic range of 6 dB from red to blue, that means that that reflection is at least 6 dB lower in terms of the contribution at the measurement spot than the actual direct sound from the source colored in red. So what is this all about? Well, if we go and take out that perforated ceiling panel, we see immediately that there's a non-insulated cable feed-through or a cable passage communicating the 2 rooms. And so there's aerial sound transmission, and we get a huge loss of transmission loss. Okay, so that's a very straightforward case done with a traditional dodecahedron that many of you might already have. We can go through the same or very similar process, this time with the tapping machine. In this case, we're separating or we're analyzing the partition between a hallway and the meeting room. The receiving room was chosen to be the meeting room. This can be reversed anyways. And so we set the tapping machine on the other side on the hallway, make it excite the floor, and measure with the sound scanner simultaneously to try to understand how the sound is propagating. In this case, again, two weaknesses were detected, this time in the 630 Hertz and 800 Hertz bands, among others. Yeah. Right. So if we first take a look at the 630 Hertz band, even with a very large dynamic range, we see that most of the sound is coming from the floor directly. So we have a source that's located directly on the floor on the side of the sound scanner. Remember that the source is on the other side of that wall and the door. So we immediately conclude that there's some sort of communication or coupling problem within the floor on one side and on the other of this partition. On the second picture, the situation remains largely the same for the second octave band of 800 Hertz, but this time we also see some contributions from the wall. Still, we have to keep in mind that the dynamic range in this image is set to 9 dB, so the difference between a red and the blue source is about 9 dB, meaning that the contribution from the walls is about 9 dB lower than the contribution from the direct sound from the floor. If we now switch to even higher frequencies, let's say 1 kilohertz to 3 kilohertz to represent the higher end, we see a very precisely localized leak on the bottom of the door. So in this case, we're dealing with aerial transmission through a leak at the gap between the door and the floor. Yep, so that's a very straightforward conclusion. We can check the coupling between the two sides on the floor. And so the sound scanner in this case helped us unambiguously identify the root cause of the problem that we were dealing with. We made these recordings in just a few seconds or minutes. And we used equipment that many acousticians or consultants already have in their portfolio. So the sound scanner will play nicely with other tools. Okay, let's see another example, this time related to noise control, specifically industrial noise control. Some of the challenges that we typically face when creating a model of a certain plant or industrial area is to find the right level of detail, meaning create a model that represents reality well and accurately, but that is not overly complex, that does not take an eternity to create, and too many measurements to fit the data into the model. We also sometimes have trouble accessing critical areas. And at some point, we need to make some assumptions about certain sources, which are not necessarily easy to make. Also, if we want to monitor multiple sources in parallel at the same time, this can also be a challenge to synchronize. We were dealing with this factory. It was generating some complaints in the residential area that we see towards zone or measurement point number 3 about loud noises coming from this industry. We chose 3 points around it. Point number 1, right on premise in front of the facade of the building. Point number 2, right outside of the building, also looking at the facade. And measurement point number 3 in the direction of the residential area. So number 3 will probably be the most critical or relevant, given that it's the one that represents better what the residential area feels or hears. So each of these recordings took between 10 seconds and 30 seconds to achieve at each of these measurement points. This is the recording time. Then there's a very short computing time, but all in all, not more than 2 or 3 minutes were needed to create each of these images at each point. So right in front of the facade, we immediately see 3 sources. Number 1 was an air intake, which was sucking air into the factory, making a lot of wideband noise. Then there's a loading zone where some trucks are idling right outside of the picture. And then finally, there's a packaging machine on the top floor making a very tonal noise. In the second picture, we see that there's a sort of a barrier surrounding the industry, some sound from the ground floor sources is leaking over the barrier, but now the dominant source seems to be the packaging machine on the top, given that the sources on the ground floor are largely attenuated by this barrier. And finally, and also most importantly, the third picture, or the third viewing angle, reveals that the loading zone is still the dominant source. So if we were on the software, we could do some frequency analysis and understand which source is radiating which frequency range. We would notice that on picture number 3, most of this noise is lower frequencies. The barrier at this distance is largely being ignored by the sources on the ground floor, and the packaging machine is now secondary once again. So if we wanted to improve the noise over the residential area, the solution would be to tackle the sources on the ground floor and not necessarily the packaging machine, even though we know the directions, it is worth considering. Okay. This is another measurement that I chose to show today. It is extremely simple, but very telling. This is a highway that's right behind that acoustic barrier, and there's again houses exactly where the sound scanner is placed. So from the point that we are looking on, this acoustic barrier is very effective all along this highway, but seems to lose a lot of its efficiency at this point. So near this overhead and traffic sign and bridge. And so the main hypothesis was that sound or road or traffic noise was being reflected on the sign and then coming through these residences. We made a quick recording to try to confirm or deny this. And we immediately saw that the source was not located on the sign at all, but it was actually located on the underside of the bridge. So the two pictures that you see on screen right now are the exact same recording. The only thing that changed between the two is the dynamic range. It is not required to make two recordings for this. This is something that you can simply adjust in the analysis phase. And so with a very reduced dynamic range, we precisely localize where the reflection was happening, which is in the underside of the bridge. And then when we increase it, we can check if there are other sources which are also affecting the level at the measurement point. In this case, one of them was a reflection of that reflection on the floor, which is about 3 dB below the main reflection, but still contributing considerably. So now we know how to proceed. If we want to tackle this problem, we need to treat the underside of this bridge, change its geometry, etc., etc. There are a number of solutions that could be applied. And we could easily return here with the sound scanner, make the same recording, and see how effective that solution was. Right. So a quick wrap up on this then. The sound scanner can be used to quickly get to a model that accurately represents reality without being overcomplicated. And it can help us make the right assumptions about some sources that we suspect are there or know are there, but do not know how to accurately quantify. We can easily document the effectiveness of these measures. We can go back to these plants, make a recording after the countermeasures were put in place, and check how effective they were. And we can also communicate easily with our customers about these decisions that we make, these conclusions that we arrive to make them part of the process. Right, so we get to the last two use cases. We will go through a traditional concert hall acoustics case, and then to a new method that we have been using lately and that we're still working on developing even further, which will try to detect or to quantify the absorption properties of a certain material or sample. But let's start with the traditional room acoustics or concert hall acoustics case. So once again, a few of the challenges are in the modeling phase to find the right level of detail without making measurements at an infinity of points in the concert hall or performance space, etc. We need to make the right assumption about the properties of the materials that are in use in this space. And of course, all of these can be extremely time consuming, complex, and there might be some back and forth process with the model and the measurements. So in this particular case, this is a real picture from this concert hall, which is in St. Gallen, Switzerland. There were some reports of very high loudness from the right side of so the people on the left side of the stage area were reporting a very high loudness perceived from the instruments on the right, and also some echoes or a delay or a perception of delay from the instruments on the right by the musicians on the left. Through a specific measurement procedure, we can obtain an impulse response by measuring the setup that we described in the picture above, so right below measurement setup. So we replicate reality by placing an omnidirectional speaker where the problematic source is, and the sound scanner where the receivers are. So we will make this omnidirectional speaker radiate a train of pulses that the sound scanner will record, and then it will compile into an impulse response. We can discuss this process a lot more in detail, but I would leave that to a further discussion on a one-on-one meeting or over email with whoever is interested. Okay, we can now break down this impulse response into a couple sections: the direct sound, the primary reflections, which are associated with the perception of loudness, and the critical reflections a little bit later, associated with the perception of delay. These specific time intervals vary according to literature, but we selected the ones that have more consensus. Of course, the user can select any random time interval for their analysis and create an acoustical image from that. But so let's focus on 3 different time intervals: 0 to 5 milliseconds, 20 to 50 milliseconds, and 50 to 150 milliseconds. So of course, the first few milliseconds are perfectly located on the omnidirectional sound source, which is emitting these pulses. From 20 milliseconds to 50 milliseconds, we notice that most of the energy is accumulated on the back wall, on the lower part of it, where a diffuser is placed. So this shape that you see on the background, that's a diffuser that has no absorption, but has some diffusion properties. And most of the energy is coming from that part. There's also some coming from the floor and a little bit from the ceiling, but most of the energy coming from the back wall. Then the late reflections or the critical reflections associated with the perception of delay are coming mostly from the back wall, but the part that is completely untreated, and also from the ceiling. So now we know exactly how to act in order to counteract any of these problems that were reported. So if we wanted to improve on the perception of loudness, we know that we have to potentially add some absorption to the back wall, to the diffuser on the back wall, the lower part. If we want to improve on the critical reflections and the perception of delay or echoes, we need to treat that wall, which is at the moment completely untreated, by adding some diffusion, absorption, or even adding some absorption to the diffuser ceiling. So those are our options. We can make those changes, come back, measure again, and see if the situation has improved. Okay, I hope that was clear enough. And now we come to our last case, which is trying to determine the absorption properties of an acoustic panel sample or a certain material sample. It can be anything. The procedure is quite simple. We position the sound scanner very close to an omnidirectional sound source, which is once again transmitting a train of impulses. These impulses will arrive directly to the sound scanner, but also bounce on that sample and come back as a reflection. We require at least 10 seconds of audio to be recorded. And once we have that reflection, we will try to isolate it in space and in time. So we will perform some spatial filtering in our desktop software to extract the spectra of that particular portion of the image at that particular time. So we can also go to the time signal, as you see on the graph on the top right, select only that reflection and not the direct sound and not the later reflections. And so we get the energy and the spectrum from that event only. So that portion of the time signal. Now that we have this spectrum of that reflection, we can reference that to the direct sound. And if we have a few samples, we can compare between them, obtaining a certain relative absorption of each of these samples in the same setup, and plot that to understand the absorption properties of each one. In this case, we realized that one of these samples was performing a lot better than the others in the low frequency range, and that one of them was performing a lot better in the very high end. So that way, if you're trying to decide between a couple of samples or even trying to understand what data to input into your model in terms of absorption, or at least the shape of the absorption curve, this is a way to get to that. This is still a relative measurement, but we are working on a way of converting this into an actual alpha coefficient. It will still be an estimation, but we are confident that we can make that happen in the short term. So stay tuned for that, which is shortly coming. But at the moment, this is still already useful. So thank you very much. We have still a few minutes left that I would like to use for questions and answers. So I'll hear you now, and thank you very much. Okay, let's see the Q&A box. Still nothing, but we can wait for a few minutes. Okay, so one person is asking what's the range of motion or the angle that the scanner can be pitched to scan in the upward direction. And the answer is as far as you need to. There's one way to set the tripod to make it look slowly upwards, but you can also simply place the scanner completely parallel to the floor and have it look completely upwards. So that is possible. The measurement position for the user becomes a little bit awkward, but it's doable still. Okay, somebody is asking if it is possible to use this to show floor flanking or airborne sound. Um, I do not, I have not personally, but I can definitely check our system and database and see if this is something that we have. I am sure that you should be able to. There's no reason to think not to, but I cannot guarantee that as I have not done it. I will check our database and come back to you. Okay, so another question for those who are already owners of an acoustic camera from Seven Bel, is there an additional cost to measure reverberation? So this suite that I showed at last, this suite of features for reflection tracking and absorption are part of the, let's say, higher end software package for higher tier. You can easily upgrade to it if you're not already on it. We can also offer a trial for that. So if somebody wants to try that, that's entirely possible before deciding on committing. Okay, so somebody's asking if there's any plans to release a larger probe than the P254. So our largest probe is called the P254 sensor. It's already 2.5 meters in diameter. So the sensor is actually half that size, but you still need 2.5 meters of clearance. And that one has a 125 hertz cutoff frequency in the low range. There are no plans, unfortunately, to release a larger sensor variant. That one is already on the limit on what's practical to use. It's very hard to use indoors. Outside, it is definitely a very good performer, but there are no plans to make it even larger for now. And whenever analyzing that low or frequencies that low, there are other methods like near field holography and intensity recordings, which will have their own drawbacks. But yeah. Okay, one more question. Have you thought about combining with LiDAR images? We have discarded that path a certain time ago, but it was definitely on the table. And so if there's any comment or suggestion on that or ideas regarding how LiDAR could be integrated, I would be happy to also hear that. Yeah. Okay, so we arrived at the end of the session. I don't see any other questions coming up, so I thank you all who participated very much. Um, Whoever wants to try out the system can reach out to us directly to organize a trial. So thank you all very much. Have a nice evening and afternoon, and I will be in touch with whoever wants to keep on discussing the sound scanner. Bye bye. Thanks.